Thank you very much, Lucy. Thank you very much for coming along. It's very exciting. Just to brief you, this talk is completely pointless. There is just no point to it whatsoever. No one cares about candles. And also, almost nothing in it is really true. It's truthy. It's truthy. Yeah, truthy, true-ish. Anyway, so this is a talk about candles, and candles are just wonderful and beautiful things. So here, this candelabra was a wedding gift 25 years ago, and when you look at the candles, you can really remember, I remember the people. Somehow they just really chime with people. They're a beautiful people-flavored way of making light. And so I just thought I'd go through, they've got a few slides to explain how a candle works, in case you don't know. So the key thing about a candle is that the flame gives out heat, and the heat warms the wax, and the wax is a solid and it melts, and you get what Michael Faraday called a cup, and the formation of this cup of liquid wax is very important. And then the wax gets wicked up the wick. That's why it's called a wick. Okay, and then it mixes in air from the outside, and then up in the flame here, some kind of sort of magic happens, some stuff happens that makes this beautiful light and heat get given off. So what's that magic? That magic is a chemical reaction between wax and oxygen, and it makes carbon dioxide and water. Now this equation, again, it's one of those things, it's not true. So just to brief you for later, it's not right. There you go. So what that looks like is, if you could imagine wax, it would be a very long molecule, pretty linear, with about 25 carbons. It's a bit variable, and the reaction looks like this. So we get some oxygen, that's the red ones, and the red ones come in and they react with the hydrogens. And did you see it left a bit faster? That means it left with a little bit more energy. So the water, it's left with water. And then lots more oxygen comes in and rips off the hydrogens, and you get lots more water given off. And then we come off and rip off more hydrogens. So this is the process that's going on in the flame. And then we've got the backbone here, and the oxygens come in again for the kill, to rip it apart from its vertebrae. Oh yeah, there we go. Wah! And you get a few molecules of carbon left that clump together to make little nanoparticles that we call soot. And those are very important for the candle, because it's those things which get hot, and it's those things that when they get hot they glow and they give off light. So the light from the candle comes from those hot little particles. If it didn't have particles, you wouldn't get light out of a candle. So I just thought I'd show you a little video of a candle. It's kind of stupid showing you a video of a candle when I've got candles here, but hey ho, this is one I took on my iPhone, which you can do slow motion with. I don't know if you've tried that, it's a great thing. And so there's just a number of things. So here's my finger coming in, and it's astonishing. You can just put it out like that. And then when I take it away, can you see this stuff? This is the stuff you think, oh, it's smoking. But look at it, it's not smoke, it's white. It's the wrong color for smoke. That is wax. Remember I said it's coming up, wicking up the wick, and it then evaporates from the surface. And what's happened is they're still hot, and you've got wax evaporating. This is fuel for the candle. So here we go. So if we bring up a light here, you can see, boom. Here we go. So you should be able to see the flame jump down. Wow, did you see it? Yeah, that's liquid, that's wax. It's kind of condensed into tiny little droplets, and that speed of that burn, that's called the flame speed. It's characteristic of the way any type of fuel burns. That's Gavin Sutton told me that, by the way. Okay, so that's the sort of picture we've got now. The air coming up, all this sort of crazy stuff going on, but there's a problem with that makes us need a more complicated thing, and it's a very simple problem for me to demonstrate. And the problem is that wax is not flammable. So, Andrew, can we switch to magic camera view?
We shall endeavour to.
So, I spent the morning shaving a candle, and can we get a view of some wax? So we will want to look at this thing here. So that's candle shavings, and can you see it melting? It doesn't catch fire. What? How can you have a candle that burns just so easily and yet the wax is not flammable? Isn't that just amazing? That's almost the first amazing thing about candles. Thank you, Andrew. That was, I'd just like to say the camera work was outstanding. And to understand why that is, you need to understand a bit more about the crazy things going on. You need to understand ye flame's structure. So here's the wick. Oh, look at that. We've got the little convection things from the... So what's happening is wax is coming up along the wick and going out. And now you can begin to understand why that wick is always the same length. That what's happening is wax is going up it and then evaporating from the surface. And then you reach a point after a little while, all the wax is gone. So the bit at the end hasn't got any wax coming out of it, evaporating. So that as the wax evaporates, it cools the wick. And so that's what keeps the wick from burning as the wax is evaporating from it. And then you reach this second zone here called the pyrolysis zone. Pyrolysis, I love the way physicists give words to things like pyrolysis, as you sort of think, oh, pyrolysis, what is that? It just means heat stuff. Something happens because of heat. It's not a chemical reaction, it's just something happens because of heat. And what pyrolysis is it breaks apart the wax molecules into smaller molecules. And the smaller molecules are more reactive. And so that's one of the key steps in making it flammable. And then the gas, the wax keeps going in its smaller molecules, and it's here that we get not complete combustion, but incomplete combustion. It's very important that it isn't complete, because it's got to leave us those nanoparticles. So what's happening here is in comes the water molecules. So this talk has some jokes in it. And just to warn you that we're coming up for a Christmas joke. And here it is. So here comes the oxygen, and here is the chemical nature of what's going to fly off there. There we go. And we get left with the carbon, backbone of carbon that forms these nanoparticles. There, and it's those that heat up in this zone of incomplete combustion. And then we go further out and we get the complete combustion. So that we get complete combustion here because the air is coming in from the outside. So here there's lots of oxygen, and when you get into the inner part of the flame where you've got the incomplete combustion, you've used up lots of the oxygen. So just think how clever that is to have a fuel which is not flammable, and yet spontaneously this process happens, breaks apart the molecules and makes it flammable. Absolutely incredible. So here we've got, this is the sort of overall picture. We've got evaporation, pyrolysis, incomplete combustion, and complete combustion on the outside. Now, one of the things about science, one of the things that makes things science is you actually look and check whether all the nonsense words you said are actually correspond to reality. And real flames are much more complicated than this. The radiation there melting the wax. So I took a picture of a flame last night. I dialed down the exposure so you could really see what was going on. And you can see here's the wick. You can just see the tip of it glowing, and it's bent over in the typical way. And then you can see there's a space here with no light coming from it, or not as much light. And so I think that's where the pyrolysis and the evaporation is taking place. It's not cylindrical symmetry, it's kind of bent over symmetry, and it's distorted because of everything rising up. And there you can see here you're kind of entering the nanoparticle formation zone. Here's the main bit of it, and then at the top you're leaving it and entering complete combustion. I'm not quite sure where final combustion is, but later on, what we'll do when we've got questions and answers is I'll ask Gavin. And that's our picture. So it's not perfect picture, but it's probably enough to be going on with. Does anyone want to ask any questions at that point? You know, we're all friends. No one cares. Yeah.
How hot is that can?
But I'm glad that's the next bit. Okay, so I thought one of the things, at MPL, we measure stuff, and so one of the things we can do is make measurements on a candle to begin to understand how things work. So let's measure the temperature of a candle. Okay, so we've got a thermocouple. So we've got a slide for this. So we're going to stick a thermocouple in a candle. Now the thing is, if you stick a big thermocouple in a candle, it cools down the flame. So what we're going to do is we're not going to do the whole experiments of doing different sizes. We're just going to stick a super fine thermocouple in a candle and see what temperature it reaches. So I've got a really, can we go to switch to camera magic again? Let's try this one. So we need to have the excellent, wonderful. So the thermocouple is very, very fine. Can you just see it there? And it just measures the temperature right at the tip. So if I put that in my mouth, it goes up. So I'm going to try and hold it in the flame, and we need to try and record what the maximum temperature is. What have we got? Can someone shout out? Did we get 1100? Yes. Wow! The answer is 1100, Jamie. Actually, it's probably a bit hotter than that. So did anyone think it would be that hot? I know Gavin did, but it's shockingly hot. It's absolutely astonishingly hot. So, and in fact, it's a big problem. And I don't know if you've looked at MPL's corporate report. Was it last year? Yes. Yeah. And Gavin's got a way of measuring the temperature of flames with a laser. And this is the reason why it matters. If you just stick a thermocouple above a burner, you will be wrong by about 900 degrees. That's a big error. So we're probably wrong by, I would guess, a couple of hundred or something like that. But still, it's very, very hot, more than 1,000 degrees Celsius. So there's something really exceptional going on in a candle. So the question is, we can ask about this stored energy and the amount of power coming off. So one nice way to work out the stored energy is to weigh it. So can we do I think we might need to move the camera thing. This is not PowerPoint, by the way. That's why it takes time. Reality is just so difficult. So can we get the scale on the... Yeah. Oh, we got the unfortunate... Okay, so 209.77 something. So what you should be able to see now after it settles down is all the products, the wax is coming off, it's evaporating and it's turning into, okay, can you see it going down? So it's just, obviously you can do this at home, you just have to take half an hour, which is an inconveniently long time for a talk. So 209.7, so it's coming down by, I think it's a couple of milligrams a second or something like that. That's very typical for a flame, 2 milligrams a second. Thank you very much, Andrew. But isn't it beautiful precision measurement, just that you can actually see it happening live? I love that. That's wax, not smoke. It's wax, not smoke. Smoke. here's the PowerPoint, which is a pretty good PowerPoint actually. I'm quite pleased with this one. There we go, and then it's going down, and then it. So if you do that, so this is one I did at home a while ago. So this is 3,600. These are hours over here. And the slope is about, in this case, was 1.78 milligrams a second. And then you look up on wherever it is you care to, what the calorific value of wax is. And you find it's about 43,000 joules per gram. That you get, it varies from one type of wax to another. So putting those two together, you can say that the stored energy in the candle I used was one of these white domestic candles here. That's a 43 gram candle, is 1.8 megajoules, 0.5 kilowatt hours of energy stored in that candle. That is phenomenal, absolutely phenomenal. The power, apparently, according to this weighing thing, is 76 watts. That's a real substantial amount of thermal energy being released. So I really did question that. So I did a second experiment, which I'll show you in a minute, but just to sort of put this stored energy in context. So if you've got a candle here, if you take something like a stick of dynamite, which is about the same in size, and you set light to the stick of dynamite, then what will happen is, boom! I wasn't allowed to do that one. And then, whereas a candle is more like this. Very, very long. It takes hours to release the energy, but it does it in a very, 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 very uniform, stable way. The material itself is not flammable, except just at the point where it's used up. So, and if you compare it, for example, with the energy in a battery, a normal candle is equivalent to 150 AA batteries. This is just a truly astonishing piece of energy storage kit. So is there really available 76 watts of power? Well, to do that we need another experiment. So what we're going to do is put some water in a conical flask, and we'll put a thermometer in and heat it up. So isn't it wonderful, aren't thermocouples wonderful, that you can simultaneously measure the temperature of a flame, and then just a few seconds later you can use it to measure the temperature of water. It's just... yes, please.
Is it live or is it PowerPoint?
It's live. Can you tell the difference? So I'm sticking in the thermocouple. I'm sticking it in now.
Oh.
So if I put that there, you might be... In fact, I need to put this on the mat here. There we go. And so what did it read? It read 19.9. I'm going to put this underneath, and we're going to wait for 1 minute, and then we'll read it again. We'll see whether it's got hotter. That is 103 point something grams of water. Anyway, so we've got about 50 seconds. Would anyone like to ask any more questions? Or you're very, very quiet. Oh, yes.
You said the dynamite went boom, and we believe you on that. But what's the energy of the dynamite compared to the energy?
Sorry, there's about 10 times more in a candle. I think it's actually factor 8 or something, but it's just about the release rate that's the difference between them. It's truly astonishing. So how are we doing for time? Another 15 seconds. Let me just give this a bit of a swirl. Can you see it's going up? I put the flame underneath the water, and the temperature has gone up. And that's 1 minute. Okay, so let's just stop that. And let's just swirl it round. Now that's actually warming up the water and the flask as well. So some of the heat is being used to warm up the flask. Can we switch back to PowerPoint? So obviously I did that experiment before as well, but what I did was I heated it up in 30-second stints and measured the temperature in between. And so the temperature went like this. It was quite linear. In that case, I had 102.5 grams of water. And from that, I worked out the heating rate, 0.132 degrees Celsius per second. And the heating power came out at about 60 watts. So from weighing it, we estimated there was about 76 watts of thermal power coming off a candle. And by measuring it thermally, we got hold of about 60 of them. But you know, there's lots of ways heat could be lost. So the amazing thing is that yes, it really is. We really are getting that much thermal energy off a candle. And then the last question we can ask about is about light. How much light are we getting off a candle? Now, you may know that the unit of light is called the candela, because we used to use candles as a gauge of light. In fact, did anyone watch Blue Planet last night? Did you see they had sperm whales? It used to be, 150 years ago, if you wanted to make one of these, which is a British parliamentary standard candle, what you would do is head off into the oceans of the world, find yourself a sperm whale, kill it, open out this stuff in the top of its head that no one knew what it did, called spermaceti. You'd separate it and you'd get this wonderful stuff that made great candles. Now, the fact that we did this at all really makes me reflect. First, it makes me reflect on how much we really must have wanted to make candles. That looks like a lot of work. Secondly, that some things in the world have got better. We don't do that anymore. So this is a British parliamentary standard candle made out of the gunk from a sperm whale's head. I'm just going to pass it round. And it used to be, we used to burn that to make a standard amount of light. But now we have a different way of measuring the amount of light that things happen. So what we do is we use the integrating sphere, connect it with the fibre optic cable to the USB spectrometer, and then take a look on the computer. So that's what we'll do now. So we'll just switch round. So here is the, this is an integrating sphere. So this is just a sphere which is painted white on the inside, and this is fibre optics. And if I open this up and let it look at the light here, oh, you can see, so that's, we must have LED lights. That peak up here is LED, typical of the blue thing that drives LED lights. But let's take a look at what the spectrum of a candle. So what we need to do is switch all the lights off. So the lights are going to go off now. No, they're going to go off. There we go. They're going to go off.
Temperature measurement, not light measurement.
Yeah, that's right. And then if I do this, oh no, it doesn't work. Okay, so we'll just try and measure the spectrum of a candle here. Now, there's not the glitches there are not significant. That's called an order matching filter on the spectrometer. The key thing I'd like you to see is just that it's a smooth curve. It's a smooth spectrum. And so that's one of the characteristics that tells you that the light has come from particles rather than from atomic molecules, individual atomic molecules. Okay, so let's switch that back. Now it's very hard to actually work out how much light there is in terms of watts. You have to go to each wavelength here and work out how much power there is. It's the kind of thing we're very good at MPL. But when you work it out, we've got about 0.2 watts of light, which tells us that candles are really great, but they're actually rubbish at making light. It's very, very inefficient. So the question is, could we do better? Okay, so when you convert thermal energy into work, you've got to get hold of some of this random motion and extract some of the energy and make it do some work. And you can't do that with 100% efficiency. So it's just not possible to get at all the energy there. But we can do various things. So here's, we've got some engines that we can use. So here's a couple of them. These are Stirling engines. and I'm going to set light to them. And what these do is take the energy, the random energy, and by sheer cleverness, so they expand the, they heat things up and cause gases to expand and push pistons, and then they use a little bit of that energy to recompress it. So let's just, so these are two devices, so that they have to heat up. Have you got any questions so far? How's it going for you? How is it for you?
No question.
No questions, okay, yeah. Oh, yeah, we can do, we go for TV. So these are Stirling engines. This one's a very cheap one that you have to make yourself. And this one's quite an expensive one. It costs £35, I think. Let's just see if this is working yet. Oh, yeah. Oh, wow. Can you see that? So we're taking some of that random chaotic motion and it's making this thing go round and round and up and down. Now, it's pretty good, but it's actually not very efficient. It just doesn't have a lot of thermal energy. This one has got a little generator on it and takes a while to get started. But so I'll just keep going while this one struggles onward. A little bit worried because this one is making stuff which is smoke. So, oh, there we go. Yeah, can you see that? Can you see that one going round? Pushing backwards and forwards, but it has. I tried earlier on. It doesn't even have enough energy to light up a light bulb in it. Not even an LED. I'm afraid I've lost the light bulb, but I promise you, it doesn't have it. If I put a light bulb in, it will just stall because it just can't do the work. Okay, so let's just take those off there. And so it's Stirling engines, very good, but so I am near the end, Andrew. Don't worry, it's okay. We'll be okay. So that's the Stirling engine, and we can do cooler things than that. We can take our thing and use a thermoelectric generator to make some, to convert things directly into electricity. So this is a toy here. So we'll just do the PowerPoint here. So we've got some ice and we light a candle here. This is a thermoelectric generator, and when heat flows through it, it drags a little bit of electricity with it that you can make go round a motor which will turn a wheel and drive the car. There we go. But you need to keep this bit cold to keep the heat flowing and stop the other side warming up. So can we switch to reality again, Andrew? I apologize for this. Whoops. I can tell you the preparing the safety case for this took quite some time. Oh wow! Do you see it?
It's in the risk assessment.
Wow, that worked better than I thought. Okay, so we can use thermoelectric generators to convert some of the energy out of a candle, and that gave me my last thought, which was this one, which was, could we actually take a thermoelectric generator, use a candle, use your USB converter, and then plug in, set that going, and then plug in a torch to make a light which was maybe brighter than the candle, which would be, I thought would be cool, and that's what we're going to do here. So that's so we need to switch back to reality again. Here's the. So let's get rid of this one. Sorry for all the switching round. Everything, reality is just such a thing. So now it's going to take about 2 minutes. So this would be a good time to have some questions, if there are any questions, because this is the last. Oh, you've got a question. Wonderful. Thank you very much.
I was wondering, the incomplete combustion
Yeah.
region changes, oxygen comes in the air.
Yeah. Oh, yes, it would. It would for sure.
Does it then affect the efficiency of converting power?
Oh, you mean could you reduce the oxygen to get more incomplete combustion? Is it burning? Okay, that's not planned. That's. So there's a little light will come on the USB thing when it's ready. Let me just go and get the torch ready. So this is the torch, which I've wired up to the USB converter here. So yeah, you could engineer candles to produce more light, I think. And it's very interesting that what the most important dimension of a candle is the dimension of its wick, because that determines how much wax is coming up. So are we happening there? There should be a little light here. So I just want you to know, is Laura here?
Yes, it's come on.
It's come on. Oh wow, yeah. Oh.
It's gone off now.
I was just going to ascertain an eyewitness had seen it work today. So there we go. If I connect that on here. Oh yeah. So if I point that, that's not bad. Okay, and that's the end of this talk. Okay, so.
Thank you very much, Michael. That was fantastic.
There you go. And thank you to all the people that helped.
Thank you to all the